What I'm going to be talking about today is a really cool theorem called Desargues' theorem that actually showed up in mathematics many years ago. We'll talk about that. And I want to talk about why I think this very old theorem has incredible relevance to today's modern world. That's what I'm going to be talking about today. Okay, first of all, I want to say thanks to you guys. The talks here really were amazing. I was enthralled. I actually learned a bunch of things that I'm going to try to take home to Franklin and Marshall and do with my own students, because you guys were really, really good. I also want to thank some people that I've worked with in the past. Mark France is the co-author, along with me, of that Viewpoints book that I mentioned. And when I say co-author, it's like I'm Sancho Panza to his Sherlock Holmes. He's really an amazing, right? That's supposed to be funny, but it's true. He's just a really amazing artist and an incredibly good writer. And he knows especially a lot about art, which helps me. Fumiko Futamura is a young mathematician down in Texas who actually knows projective geometry, which I've just started learning really recently. That's not what I was trained in. And Stephanie Douglas is now a graduate student in astrophysics, but she was an undergraduate who did some research with me and helped me to learn what Desargues' theorem is and led me to try to understand it from the point of view of an artist. All right, for those of you who already know all this and just think you're going to get bored, I actually have a puzzle for you to play with if you want to try sketching. So imagine you're sketching. This is a beautiful picture. This is sort of what it looked like outside my window this morning, the snow and the sky. You could add a little color if you have coloring crayons so you can see, right, ground and sky. And what we're going to do is we're going to put in here a road like this that looks like it's going back into the distance. There's this vanishing point. Yesterday we talked about why there's a vanishing point. Here's a puzzle for you. If this is not a road, but a railroad track, then you could put down the first railroad tie there. And I'm actually going to make the puzzle easier for you by making it weirder. I'm not going to put the second railroad tie. I'm going to put the third railroad tie. So that's the first and the third. And a good question for you is, where does that middle railroad tie, where does the second railroad tie go? Right? It probably goes closer to the third one than to the first one. But how do you know exactly where it goes? I think this is an interesting question. Right? I think that's a question that artists would like to know. As a matter of fact, artists would like to know not just about that one, but where all the other ones go too. And once you see the answer, you go, oh, that's beautiful, and you just want to keep practicing. You want to keep drawing it. This railroad question is, in some ways, so much more accessible and compelling than the train A leaves Kingstown, Rhode Island at noon heading, the one that scares everybody, the two trains question. So that's something for you to play with. While I'm talking about some other stuff. So what am I going to be talking about today? I'm going to be talking about this. Oh, hang on just a second. I'm going to be talking about how I came upon this. So so grad school. This was my first picture of grad school. This is really first. So okay, for those of you who are headed for grad school, I have bad news and good news. And the bad news is that the first year of graduate school was the worst year of my life. And the good news is the first year of grad school was the worst year of my life. It gets so much better after that. Your first year, you just feel like you're the stupidest person on the planet. If you quit then you've endured all that pain for nothing, because by the second year, things start going really well again. So what do I remember from later on in college? Aside from this, I remember this, okay? All the friends that you're making in college, you'll be good friends with many of them forever and ever, but the friends that you make in grad school, you just see all the time. We go back to math meetings and we see each other. So it's this incredibly bonding experience of people who are going to be your friends for life. All these really cool people that I got to meet, my advisor and a bunch of others. While I was in grad school, I got to meet two professors who really, really influenced me, even though, when I was in grad school, their fields had nothing to do with my field. One of them was a guy named Bob Devaney, who's actually now the president of the MAA. I got to go to a summer workshop that he did. He was not actually in my department. He was at Boston University, and I was at a different place. You can see I put him on this pedestal, right? He's amazing. Back when I was in graduate school, people were starting to talk about doing research with undergraduates And chemists could do research with undergraduates because you could put undergrads in labs and then teach them the stuff as they went along. But all mathematicians said, there's no way an undergraduate can understand my research without having first gone through graduate school, which would make them not undergraduates. But Bob Devaney said, well, there's this cool area called chaotic dynamical systems, and I think you can teach this to people with just calculus. So he started bringing this really esoteric research field down to the level where undergraduates could actually work on interesting projects. And he did this with the aid of computers. The amazing thing is not only did he help undergraduates do research, but by doing this, he transformed the area of dynamical systems, that whole research area. He shaped the future direction of it because all these cool undergraduate questions made the big, decent researchers scratch their heads and think, how would you do this? So it was really, really cool what he did. There was another professor who did very similar things. There's this guy named Tom Banshoff, who also, by the way, was a president of the MAA. Banshoff studied the fourth dimension, and he also was using these newfangled computer programs to sit students down and work in front of a computer, try to draw these really cool pictures of like hypertori and stuff. He's also on a pedestal for me. And he also was getting undergraduates involved in research, trying to understand these things that mathematicians were having a hard time wrapping their heads around. So I decided I wanted to try to do that too. I actually think that projective geometry is ready for this kind of transformation, where you take this deep research field and you use undergraduates who ask these really good, naive questions that make you think of the world in a different way. You put them in front of computers, which nowadays we can do really cool computer graphics, and it transforms the kind of research questions we can ask. So this is what I want to be. I want to be like them, but with projective geometry. So what I'm going to show you today is an old theorem that we can breathe new life into it by using drawing tools, both ruler and pencil, but also by using computers and playing around with pretty pictures. Okay. So this is the first ever picture we have of Desargues' theorem. We don't have a copy of Desargues' original manuscript. He wrote a lot of different kinds of manuscripts. Most of them are lost. He had this acolyte, this chief member of his fan club, this guy named Bosse, who drew this picture in one of his books. And this picture shows, you don't have to understand this yet, this picture shows that two triangles that are perspective from a line are perspective from a point, obviously. Right, I actually think this is a really confusing diagram, and most other people do too. What kinds of things do we have from Desargues himself? Well, he liked to do math, geometry. He also liked to try to draw some pictures of art. This is one of the few booklets that we do have of his. It's in the Museum of Modern Art. It was actually uncovered fairly recently. This is a little booklet, 12 pages long. The title is almost longer than the book. The title basically says, how to draw this thing without using a vanishing point. So we know that Desargues was interested in drawing and perspective. He was also interested in geometry, and they probably informed each other. Many projective geometry books that you see will say, oh, artists use projective geometry, and projective geometry was influenced by art. There's actually not a lot of evidence that these two things were brought to bear directly one upon the other. As a matter of fact, it's considerable evidence to the opposite, in spite of the fact that Desargues wrote both of these. So I think that we really are sort of forging material by bringing them together. Desargues' work was lost for an incredibly, incredibly long time, right? This is from the 1630s. It wasn't until 1812 that people started saying the name Desargues again. Now, when your professors are telling you good reasons to become mathematicians, good reasons to study lots of math, I'm sure they've given you lots and lots of good examples of why you should do this, but I bet they haven't hit upon this one reason to become good at math, which is, suppose that you are a French soldier who is captured by the Russians and thrown into jail for 2 years with no pen or paper or anything to think about. What do you do? Well, you could write a math book that becomes a textbook for generations. They haven't tried that one on you, right? No, but that's what happened to Poncelet, this guy. So he didn't just live from 1812 to 1814. That's when he was in jail. And he wrote, and just having nothing else to do but think, which is a lovely, lovely thing to be able to do, right? An enforced sabbatical. he decided to write this really lovely book on projective geometry where he harked back to some manuscripts that he'd seen by Desargues. And so it was Poncelet who made people think about projective geometry again. If you're interested in a kind of history of projective geometry and perspective and people who did some really good work on it, there's one book in particular that I think is really amazing. Kirsty Anderson really, really knows her stuff. It's very hard to find mathematicians who actually know stuff about art, and it's very hard to find artists who know a lot about projective geometry. She's really, really good. If you want to know about Desargues himself, you can look at Field and Gray. There's another good book. They're both very scholarly books. If you actually want to see a little bit about art, I showed you this other book that you can get right here. Okay, so this is the review. How many people were not here yesterday? Okay, so we've got a couple. So for those who weren't here yesterday, let me just show you the goal. For those of you who were, you can sketch the railroad tracks. What happens when students don't know geometry? A lot of my students come into college actually being really good at math and really bad at art, which is the opposite of what I thought. When I say really bad at art, I mean that my 18-year-olders are drawing like 6th graders because that's the last time they had an art class. So they draw things that they're really embarrassed about. In order to make me understand what's going on, they have to label pictures. They really want to give me a sense of 3 dimensions, and they really cannot. They struggle, they're hurting, it's painful, it's embarrassing. And by the end of the first semester, learning my math class, they get to do things that are really beautiful. They're no longer embarrassed. When they label things, they're proud of it because it's my building. And they really do manage to get a sense of 3-dimensional space. And I claim that that stuff that they're learning, it looks like they're learning art, but I claim they're really learning math because these are the problems that they solve. This first question that I'm going to ask is a question we're going to look at today that has something to do a little bit with the Desargues theorem. This is Kara's question. How did she know that all those angles that she drew represented angles that in the real world are 90 degrees? We'll look at that one today. Another kind of question that you could ask is, that we're not going to look at today, but it's like that railroad puzzle that I gave you. How did Sid know to place those towers right there in the middle? That's like, how do you know how to make that second railroad track if you have the first and the third? And given all this repetition that's going on here, things going back into the distance, how do you keep the railroad track going? That is, how do you know that those tiles are the same size going back into the distance? Those are just 3 examples of really interesting questions that you can ask if you know enough art to know that those are interesting questions. And they have a lot of really cool math in them. Okay. You'll also see that over the course of the years of learning this stuff, I've learned to do a little bit better than art. We're not going to have squirrels or Odin today. Thank God. Okay, so let's figure out how do we understand how to do this. We're going to learn about projection from a point. So what we're going to imagine is there's this person, there's Kara. Kara is looking through a window out at the world. And light rays from objects in the world travel in a straight line, bing, to her eye. And this is a line of sight right here. The plane that she's going to be drawing on is a picture plane. So where this line intersects the plane, we're going to put a little blob of paint right there, plane and a line intersecting a point. So this is how she's going to draw. Every single light ray that comes in will intersect the plane in one point. She'll put a little blob of paint down, and that's how she's going to draw the picture. In projective geometry, we actually call her eye the center, even though it's off to one side. That's called the center of the projection. So we've got an object, and we've got an image, and we've got the center. And in this diagram that I showed you, which is the same one that I sort of showed you yesterday, although yesterday it was with a squirrel, they come in this order. But in mathematics, you can mix up the order of these things a little bit, and it even sort of makes sense in some physical settings to change the order of these things. So for example, here's another kind of projection. Yeah. You like this? Okay. Here's the object. The image is over here, and there's the center. Okay? So again, projection from a point. We could also mix up the order in a different direction. We could actually put the center in the center. What would that mean? It would be something like this, right? If you have a pinhole camera, or really your camera, then you've got the object over there, and the center is in the center, and the image is here, and it's twisted around and upside down, okay? Sort of cool. And you're wondering, could we do anything else? And you're probably thinking no, but you know, in math, things can get a little convoluted. So I just want to point out that there really are things you have to be careful about, because in math, right, not a physical world, you can have projections that look like this. So here's the center of the projection, and we could say this is the object right here. Some of the object is above the center, and so it's going to project down like a pinhole through the center down here, okay? And some of the object is below the center, and it projects like a shadow down over here. And there's nothing physical that acts like that, but in a mathematical world, we can definitely have things acting like that. So you've got this triangle projecting to something that sort of, it splits up, or if you're really mathematical, you can think of this as, this thing down here is a giant triangle that just wraps around infinity and comes back, so it really is still a triangle. But it's sort of weird. So, so in projective geometry, we actually don't look at the middle of the triangle. We don't even look at points along the edges like this. In projective geometry, we think of the triangle as just 3 points and 3 lines. So this doesn't count as a point on the triangle. The triangle really has these 3 points. And I drew line segments, but we really think of the 3 lines, the whole lines. And I will draw line segments because it gets confusing if you draw the whole lines, but we think about the whole lines. So a triangle is 3 points and 3 lines that intersect in the right way, okay? And once you have this idea of a triangle projecting to another triangle in a bunch of different ways, then you can actually look at what we mean by a projection. So here, so we can say we have 2 triangles with vertices A1, A2, and A3, and B1, B2, and B3. They're going to be a perspective from a point O. O is that center, it's like your eye. If the points O, A1, B1 are collinear, and O, A2, B2 collinear. And notice we don't even care about the lines, we just care about the points here. Okay? So that's what it means for 2 triangles to be perspective from a point. Is there some kind of light fixture that shines in a weird mathematical way on them? Now, in projective geometry, anything you can say with points and lines in that order, you can say with lines and points in the other order. So there's this other sort of weird definition about what it means for 2 triangles with those edge lines to be perspective from a line. It means the lines L, so we call L the axis for a reason that you'll see in a second. If the lines L, L1, and L2 meet together, or L, A1, A2, B2, yeah, those to meet together, and L, A2, B2 to meet together. So what would that look like? Let's look at a picture. So I'm going to show you another triangle. This is a triangle from my home state. There's Lancaster and York and Reading, right there. Cool. And what I'm going to do is, oh, and we have a lot of cows, so we've put a cow there. I like cows. So I'm going to put a mirror down on top of this. Okay. So there's the mirror. See this? And I claim that the mirror and its image, the triangle and its image in the mirror are perspective from a line. Which line? This line, because like these 2 lines, A1 and B1, meet together along the line L, and A2 and B2 meet together along line L, and A3 and B3 meet together along line L. Okay? Okay, so that's really cool. We're going to keep going with triangles because in projective geometry it's really hard to draw cows. So bye. So we're ready here for Desargues' theorem, the big theorem that we're talking about today, which says that for triangles, these 2 definitions are equivalent. 2 triangles that are perspective from a point are also perspective from a line, and vice versa, which is really cool. So let's go back and look at Boss's beautiful diagram that says that there's 2 triangles that are perspective from a point or perspective from a line. Which 2 triangles did he mean in there? There's a heck of a lot of triangles. He meant these. It's really hard to see them. Do you see? There we go. Back and forth a couple times. They're there. They're well hidden. This is one of the problems, by the way, with math books, is that the triangles that we draw are really hard to distinguish from all the other garbage, really, that we're drawing. So there's the 2. Okay, so those are our 2 triangles. We need a little bit of art in our math books. They are perspective from a point. What point are they perspective from? They're perspective from this point. So notice this is a kind of projection that we didn't even look at before. Like in some areas, the red triangle is the shadow of the blue triangle, and in some areas, the red triangle shades the blue triangle. So they're perspective. You could say they give you the same shadow, if you will. Okay, so these two triangles are perspective from the point H, and they're also perspective, says Basse, from a line. Which line? This line right here. Okay, because you can see the left sides of the triangles meet along that line, the yellow line, and the front sides of the triangles meet along that line, and the back sides of the triangles meet along that line. So we've got two triangles, perspective from a point, also perspective from a line. You can also see that it's really helpful to think about these triangles, even though we're drawing them on something flat, to think about them as actually existing in 3 dimensions in 2 completely different planes. And this line where they intersect, in some ways we think of it as the intersection of those 2 planes. That's a really nice geometric interpretation to give to this picture, and it's one of the interpretations that helps us to try to understand art. Okay, so let's actually see if we can, well, let's see. First of all, I'm going to give you a really sort of silly intuitive proof of this. The proof basically uses this idea of intersections. It basically uses this. If you have a line on the glass and you extend it to the edge on the ground, then it's going to meet its shadow there. That works for every single line that you draw. And if it works for one line, then it works for any 3 lines that you can get. So you can get something beautiful like this. And right, and if we drew all these lines in this picture exactly the same way, and if we didn't have this pane of glass right here, it would be a very difficult subject to interpret, which is why it's so hard to read these math books, and it helps to put a little bit of art in them. This, by the way, was the poster for Math Fest a couple years ago. That my colleague Mark did this, and I just think it's really pretty. So, okay. So let's use this to try to draw something cool. So what I want to try to do is I want to try to draw the shadow of a kite, right? This is a good art problem. So we've got the sun, we've got the sky, we've got the ground. We want to put a kite in there, and then we're going to try to draw the shadow. Okay. So here's a kite. Oh, and I added an airplane, which I'm going to take the airplane away because honestly it was so hard to draw that airplane, really. But the kite I can do. So there's my kite flying around being towed by the airplane. And I'm going to take the plane away, and I'm going to try to draw a shadow on the ground. And that shadow looks wrong, and it is wrong. I'm not trying to trick you about that. It looks bad to me, and it should look bad to you too, although it's really hard to figure out why it looks bad, right? If you don't have math, you just go, ugh, that just looks wrong. It looks to me like the kite is flat, but the shadow curves, doesn't it? So what's going on with that? Well, maybe it's that the kite and its shadow don't really line up from the sun. But they actually do. Do you see those light rays? They hit just perfectly. So it's not that the shadow is sort of in the wrong place. There's something else that's going on. And the thing that's going wrong is that we're not paying attention to Desargues' theorem. That is, if this kite lies in a single plane, if it's planar, which is a good question, not all kites are, and if the ground is planar, which is another big if, but suppose those things are true, then the plane of the kite and the plane of the shadow ought to hit each other in a single line, right? And so when we extend the lines of the kite out and we extend the lines of the shadow, they also ought to meet, those intersections ought to meet in a line. But when we do extend those things out, we see the intersections don't meet at all in a line. That's what makes this look bad. All right. So how do we draw a shadow? Well, without other information in the picture, the first line or 2 maybe, we get to just guess. We get to just make it up because it's our picture, right? If there were other information about where the kite is, then we would know something. But we do know that the first edge of the shadow has to lie between these 2 light rays, right? So let's just plunk down one line segment right there. But by plunking down that one line segment, we already have another crucial piece of information. What's the crucial piece of information? If you imagine that that kite is really a flag and the flagpole extends down to the ground, then the shadow of the pole has to meet the meet the pole itself along the ground. So we know one point of intersection of the plane of the kite and the plane of the ground. Okay. Let's draw one other edge of the shadow. So there's another edge of the shadow. And notice by doing that, we can do the same thing. We can extend the kite down, and so we know where the shadow of the edge of the kite meets that edge of the kite itself. And actually, these two little line segments are enough to tell us everything else, because from here on in, it's just more construction. Those 2 points there of intersection tell us where the plane of the kite hits the ground, right? That's what we call the axis. And using that, we can extend the other edges of the kite down to that line, and then we can just start drawing lines out from those points there to points that are already on the kite, and drawing light rays, and everything else is from there predetermined from the first 2 edges. Once you draw the first 2 edges of the shadow, everything else is done, and there's where I'm going to put my shadow. Okay? And if you look at this, I claim that this looks like a much more reasonable shadow than that first one we looked at. There's the first one, right? Doesn't that look curved? But there's the second one we did. Much better. Cool. All right. So I like this. I think it looks good. So we'll put the plane back. Beautiful shadow. And let it fly away. Okay. So there's something very useful if you ever get a job drawing shadows of kites being pulled by planes. You will know how to do this. Are there any other applications of Desargues theorem? Yeah, actually there's a lot. So let's look at another fun one. Maybe on a day like today you are thinking about the beach, or you're not thinking about the beach, but let's pretend we're thinking about the beach. The weather's going to get warm, and you go to the beach and we say, let's draw some beach towels on the beach. So then you could say, oh, when I draw the first one, can I draw the second one so that it looks like it's the same size beach towel? That's a good question to ask, right? Why am I choosing beach towels? I'm assuming they're planar. It's hard to think about things that you want to draw that are planar without adding in other stuff, so good. Okay, so there's going to be something that looks sort of like a beach towel. And one of the questions that you could ask is that actually a picture of a beach towel? In other words, is this really the picture of something rectangular? Because it itself is not a rectangle, right? It's some kind of a weird quadrilateral. In order to understand everything that we're going to be doing, we're going to need to look at this from a bunch of different angles. So if we looked at this particular picture from above, we would see that we look at a rectangle. And remember that I said in projective geometry, we don't just think about line segments, we think about lines, right? So there's these lines, there's pairs of lines that are parallel to one another on the edge. That's an important component of a beach towel. And if we look at the artist drawing this picture from the side, we see this is Kara looking at the beach towel. Oh, so this is Kara from the side. This is not a fish. This is Kara from above. Just like Sid, I had to label everything, right? There's a ponytail, and there's ears, and I can't tell my left from my right. So she looks out of her nose, the top view, just in case we need an homage to Sid. Here's an object, because he labels everything objects. Okay. So we make this lovely claim. Some of you guys got to see this yesterday. There's this important component of looking at lines in the real world, which is that if we extend the lines of this towel like this, there are some directions where Kara can look and she can see the lines. If she's looking at the lines, she can see them. If she's not looking at the lines, she can't see them. Okay? So when is the first time she's not looking at the lines? You can see when she's looking down, she can see the lines. When she's looking up, she can't see the lines. When does she not see the lines? Does anybody remember from yesterday? When she's looking parallel to the line appears to vanish. There's a place on the picture plane, which is where her line of sight is parallel to that towel in the real world, that the line appears to vanish. Now, in this particular instance, we have drawn the towel so that the lines on the towel are not parallel to the picture plane, so all of those lines will have vanishing points. But these two lines, because they're parallel to each other, when she's looking parallel to this one, she'll be looking parallel to that one, so when she can't see this line, she also can't see that line, so they will vanish in the same place. So this particular beach towel actually has 2 vanishing points, even though there's 4 lines. And there they are. So if the thing that we drew was a beach towel, it ought to have 2 vanishing points. And we can go ahead and we can look at it and we can say, look, there's these vanishing points out there on the horizon. So notice that I'm assuming that the beach is perfectly horizontal, right? It's perfectly level right there, so that these guys vanish on the horizon. So obviously the beach is going to have to like drop off to the water later on, but that's harder than I want to deal with. Okay. All right. So this thing is the image of a rectangle. All right. So I want to draw another beach towel on the same beach that is the image of something that's the same size and the same shape. And I'm actually going to make it a little bit easier on myself, which is that I also want it oriented in the exactly same direction. So imagine that we're sun worshipers and we're both pointing towards the sun. This is just going to make the math that much easier, because really it's hard to turn one beach towel. So I want 2 beach towels, same size, same shape, and oriented the same direction. Because they're oriented the same direction, then I've got 4 sets of lines that are parallel, or sorry, 2 sets of 4 lines that are parallel. So we'll still only have 2 vanishing points, and there's a picture of 2 beach towels with the same vanishing point. Okay. And I'm going to claim that these 2 are, this is a correct drawing, that these are 2 beach towels. This is the image of 2 beach towels that are the same size and the same shape and oriented in the same direction. They look incredibly wrong. And some of you guys know why they look incredibly wrong, but I'm going to keep working with this, and then I'm going to deal with the wrongness. But I'm going to deal with the rightness first, and then deal with the wrongness. Okay. So, first of all, this pink one looks like it's skinny and long compared to this green one, which looks like it's short and fat. Maybe they're really different proportions. How would you know if they're different proportions? Well, let's go look again from the top. If the beach towels are actually the same shape, that is, if they're similar to each other, let's not deal with size, let's just even deal with shape right now. If they're the same shape, then the diagonal lines on the top of them ought to be parallel to one another. And those lines that are parallel to one another will therefore have images in the picture plane that have a vanishing point, a common vanishing point, because when I'm looking parallel to this orange line, I'm also looking parallel to that orange line. And those orange lines are horizontal, so they have to vanish somewhere on the picture plane. So if we look at this picture here, we can actually see the diagonal lines really do vanish to some point that's on the horizon. So this is my mathematical proof. It's not an emotional, intuitive proof yet, but it's my mathematical proof that these are similar shaped towels. They might not be the same size, but they're images of similar shaped towels, because that orange point sort of tells me the shape of the diagram. Okay, well, maybe they're different sizes then. What's wrong with this? Well, before we get to the different sizes, I actually want to point out, we have a line up there, the horizon, that has, like this triangle, has one line going to that point, and one line going to that point, and one line going to that point, and this triangle also has one line going to each one. In other words, this triangle and this triangle are 2 triangles that are perspective from a line. They're perspective from the horizon. Ooh, that's like Desargues' theorem backwards, right? We've got 2 triangles that are perspective from a line, and therefore you could expect that they're perspective from a point, right? So let's think about what that means for these beach towels. If the 2 beach towels are actually different sizes but the same shape, then what happens is when we connect the corners of the beach towels, the lines from the corners will meet at a point somewhere on the ground. Right? Therefore, if I draw another beach towel like this blue beach towel that I'm about to draw here now, that's a beach towel right there that I claim is pointing in the same direction. Why? Because the direction lines are going to the same vanishing points. And it's the same shape because the shape lines are vanishing at the same point. But that blue beach towel, I claim you can tell, is a smaller beach towel because if we connect the corners connect to some point that's on the ground, okay, not off on the horizon. Okay. But what about that pink one over there? Is that the same size or is it a different size? Well, if it's the same size, when you look at it from above, these lines are all parallel. The lines that connect the corners are all parallel to one another. And most of us would say that that means that these lines don't intersect, but in projective geometry, we don't like saying that two lines don't intersect. So we say they do intersect, they just intersect at a point at infinity. We're special, we have extra points that you guys don't have, right? So we have this point off at infinity where these lines intersect. It makes sense in the axiom system that we're looking at. So, but notice, because they're all parallel, their images really will intersect, right? When I'm looking parallel to this guy, I'm going to be looking parallel to that guy and parallel to that guy. So those images really will intersect at somewhere on the horizon. It's really hard to fit that all in the picture, so I had to make the picture a little smaller. But you can see that when I shrink the picture down, you can see the corner points all meet up on the horizon. So to me, this is saying, this is proof, mathematical, that those two beach towels are images of two beach towels that are the same size, as well as the same shape and pointed in the same direction. So that's my beautiful picture of two beach towels. It still looks wrong. So mathematically, we're supposed to be happy, but in our gut of guts, we're unhappy. So here are three explanations, sort of more artistic, but mathematically artistic explanations of why this looks wrong, even though it's right. Okay. Here's the first one. If we have a picture that has a lot of lines in it, you notice that the pictures that my students drew all had lots and lots of lines. That's very, very much on purpose. If the picture has a lot of lines in it, it'll look right. This looks like a picture of a bunch of squares in a room, right? A tiled room, sort of. And notice that if I color in some of the squares there, this is a 1 by 2 rectangle, and that's a 1 by 2 rectangle, and it looks reasonable to us that those two are the same shape rectangles. Even though, if we took away the lines, you could see that the green one would really look short and fat, and the pink one would look long and skinny, right? So adding extra lines really helps, and the beach doesn't have enough lines to give us more clues. So that's part of the reason. But there's still got to be another reason. So here's another way to try to convince you that the thing that I drew is really correct, even though it looks wrong. And this is one that you have experienced yourself, I'm sure. So imagine that you go on a trip to some new place, and you get this beautiful view. Maybe you get the gorgeous picture of the Rocky Mountains, or you're there on the edge of the Grand Canyon. You can say, wow, this is gorgeous. This is beautiful. I'm going to take a picture. You whip out your camera. Wait until my friends see this. It looks just like a calendar. And you take a picture. Oh, this is going to be great. And then you get home and you print the pictures out. And you tell your friends, this is not what it looked like. It was so good. Has that happened to you? Yeah. Okay. So why is this? It's not like you say, oh, my camera broke. It did the wrong picture, right? And it wasn't Professor Crannell came and jinxed my camera and made it look bad. Right? What's going on there? Your camera lens is really close to the film. When you print out the picture, your eye is really far away from the film. There's something going on that makes it feel bad. And the problem is the viewing distance. If you actually took this picture, you would look really goony, but it would be worthwhile looking this goony. If you took your picture and you closed one eye and you brought that picture in really close, you would go, oh, wow, no, this is really what it looked like. Okay? It would be so cool. You should do this with your pictures sometime. You should try that. Okay? Because no, it's an amazing feeling. Okay, so let's look at that. So here's the truly mathematical and hopefully emotionally satisfying reason about what went wrong. Okay, so here's Kara. She's out there on the beach. She's drawing pictures of the beach towel. She finishes her picture after hours of labor. She rolls up the beach towel. The beach towel goes away. She brings her picture to me. She hands her picture in to me, and Kara goes away. What's left? What's left is this, the picture. That's all we have. Okay, where was the beach towel? Even more interesting for us, where was Kara? How do I know that just from this picture? It's sort of hard to tell, right? But if it really was a picture of a beach towel, then I can start making some guesses. Like maybe the beach towel was there. And if the beach towel was there, then her line of sight through this vanishing point had to have been parallel to this edge. So she had to have been somewhere along this line, right? And her line of sight through that vanishing point had to be parallel to this edge. So she was somewhere along this line, which means she must have been there, if that's where the beach towel was. I don't know that's where the beach towel was, but if it was there, that's where she was. Okay? What if the beach towel was somewhere else? Maybe the beach towel was, say, over there. Okay, well, if the beach towel was over there, then her line of sight had to have been parallel to this, and also her other line of sight had to be parallel to that, so she was over there, which is a different place. And what if the beach towel was someone else? What if it was over there? Well, then Kara was over there, or there, and she was over there. But you notice, as I start drawing these different beach towels, that the locations that Kara could have been standing on seem to be forming some kind of a curve, don't they? And in fact, there is a mathematical name for this curve that happens. It's an interesting phenomenon because we know that her line of sight here and here, that these two lines have to be perpendicular to each other, and these two lines have to be perpendicular, and those two lines have to be. So there's some kind of a curve that has this property that when you draw lines of sight to the two vanishing points from that curve, you get 90-degree angles. Does anybody know the mathematical name of, yes? Yeah, have you heard of a semicircle before, anybody? Yeah, so there's this theorem that you learned in geometry, and you're saying, why do we have to learn this stupid theorem? Right, so this theorem that says that if you inscribe a triangle inside a semicircle, then the angles are 90 degrees. Why do you have to learn this theorem? Because when you go to an art museum and you look at a piece of work, a perspective work that's in two-point perspective, you want to find the two vanishing points, and you want to be standing somewhere on that semicircle, somewhere on the hula hoop that goes through those 2 points. That's where you want to stand, because then the picture will look really good. What happens if you're not on that semicircle? Like, what happens if I'm standing way back there? Well, then the picture looks distorted, like that, right? See, because it looks like this line of the beach towel has to be going in this direction, and that line of the beach towel has to be going in that direction. It doesn't look right. And the problem that we have with this picture that I drew for you, I put the vanishing points, remember that, really close to each other. Why? So that I could actually draw them, because I didn't want to draw the vanishing points outdoors because it's cold outside. But you guys are not on the semicircle between those two vanishing points. If you were on the semicircle, it would look really good. You're in the wrong place, okay? So what I'm going to do is I'm going to tell you the beach towel theorem. I'm going to do this construction for you in a mathematically easy way that looks bad, and then we're going to do it again really quickly in a way where the vanishing points are way far apart, and then the beach towels will look good, okay? So here we go. The beach, I don't know if anybody else has ever published this, but the beach towel theorem. Yeah. So, yeah, given a beach towel on a level beach, a second beach towel of the same size and shape and oriented in the same direction is completely determined by the closest corner. Okay, that's the beach towel theorem. Are you writing that down? Okay, here we go. So here's the construction. We've got a beach towel. We know the direction lines, and we know the shape line right there. So I'm going to give you the closest corner. It's going to be a little pink dot. Ready? Look. Whoop, little pink dot. Okay. So what do I do to start drawing this? The construction is, first you draw to the 3 direction lines. Bing, did that. Okay. And then we're going to connect this corner, and the vanishing point will give us the size point that will be on the horizon. So there's my size point over there. Notice it's way off the edge, but that's okay. From that size point, I can draw back over to this corner back here, and that's going to give me the back corner of the pink towel. Does that make sense? So here we go. Here's the back corner of the pink towel, and then I just finished drawing a bunch of lines to vanishing points and so on, and that gives me 2 beach towels, the same size and the same shape, oriented in the same direction. That looks really bad because the 2 vanishing points are so close together. So let's do the same construction here, moving the vanishing points just way, way, way far away, and then zoom in on this picture and see what happens. Ooh, that looks nice, right? That's the beach towel theorem. Now, this leaves lots of really interesting questions for the future, like, what happens if one of the beach towels is not pointed towards the sun and turned in a different direction? Ooh, that's a good question. You could imagine that actually happening, say, on a beach, right? Another question, what happens if one towel is on a piece of ground that tilts? That's a little bit harder to think of in beach towels, but you could imagine if you're drawing on a building and you're drawing a bunch of windows, and you turn the corner, you want the windows on the other wall to look like they're the same size and shape and pointed in the same rough direction, right? So how would you do that? That's another really good question. Or, for those of you who have little brothers and sisters, or like me who have little kids, you could imagine that this next question might be very important. What if your two kids are fighting and you need to be right in the middle of them, exactly fair, not closer to one than the other? So how do you place your towel exactly in the middle? And tell them, cut it out, right? Lots and lots of good questions. And the answer to every single one of these questions lies in projective geometry. And projective geometry lies in the Shadow of Desargues. Thank you very much. Yeah, you have to be a little bit of a detective. So sometimes you can see something like there's windows on one building that are sort of parallel to you, so you can tell the dimensions, and so you can tell the dimensions of the windows going back into the background. Sometimes when we do this with Spider-Man posters, which are great, we've got Spider-Man crawling up a building, and we can use his size, because he's a person, right, to figure out the size of the windows, which are like 1 by 2, so we can use that to determine viewing distance. That's a really good question. I've heard, I haven't seen this, that if you go to Italian galleries where they have these lovely old perspective pieces, there will be a tile on the ground that's a different color that you're supposed to stand there, and it feels like it's in 3D. We like to go to actual museums with our students, and we take along our chopsticks, not to poke the pictures, but to be able to tell where the vanishing points are. There are often things like squares, because there's tiled courtyards and stuff that you can determine the viewing distance. And occasionally, when we've realized that the correct viewing location is like down here on one knee, or you're standing up really high, curators come over and say, "What are you doing?" And they rehang the pieces at the right height so that people can actually see it better because of what we've done, which is really satisfying. So, yeah. So yes, so you can tell. It takes a little bit of practice, but it's a lot of fun to do. And when you get to that place, it's just so amazing to be in the picture along with the characters. Anything else? No. Thank you guys for a wonderful conference. This was so much fun. Safe travels home.